Go ahead and get started. So exam quiz 3s tonight after class, so 3 o'clock to 10 o'clock. You need 15 minutes, right? It's going to be 5 questions, same process as before, so you should be familiar with that. Exam 3, just so that we're aware, this is coming up, is on December 2nd. Okay, again, similar process. I added the learning outcomes to the last 2 sections, so the alpha carbons and the amines. We finished the amines on Thursday, so that will be on, it's not on the quiz, but it will be on the exam. Okay, so what we did on Thursday isn't on the quiz. Today, we're going to start in organometallics, so that's the next chapter. And we might be able to actually finish this today. We actually, we don't have many lectures left. So with the test, we're only talking today and 3 more. So, and the last one's going to be review. So organometallic compounds. So we've already seen some of these. We've seen the organolithium. We've seen the organomanganese. We've seen the cuprates. So we've already seen this group of organolithiums, these compounds. So those are all reviewed. The new ones we're going to see some organozincs. We're going to be using some catalysts like palladium. We're going to use some borane compounds. Another one I'm forgetting. 10. So these are pretty easy. So this is known as organozinc. These 2 are just palladium catalyst. Right here we have organoborane. And we have an organo-10. Now the main reaction for most of these, for the first ones we have, for the manganese and the lithium, we have nucleophilic attack type reactions. For the rest of these, including the cuprate, the zinc, the boron, the tin, we're going to be using some coupling reactions. Okay, so the first group we're going to be looking at are nucleophilic reactions, and then the second group are tin. The preparation of the lithium. We take at least 2 equivalents of lithium metal. I like to put it plus. The book doesn't show with the minus and the plus. The one that we may be familiar with is the butyl lithium. So this is how you make butyl lithium. And again, I tend to put the negative and the positive. So if we take lithium and react it with that, we'll end up with butyl lithium. Butyl lithium is a great base. For Grignards, right, that's my organomanganese compounds. Here, if we take our halide, react that with manganese in ether or THF. And we get the magnesium inserting between the alkyl group and the R group. Put a PR there, right? We get that. So we're familiar with both of these, or we've seen these before. We can use these as strong acids. Drop the S. Strong acids. I mean, strong bases, sorry. They're going to react with acids. And of course, this is what we see, right? If we had butyl lithium, now, if we react this with an alcohol, right, it's going to form the base. Those give me butane. And really, for the lithium reagents, this is what we see. These tend to be right. We could have butyl lithium with ammonia. Ammonia. We'll make the amide, right, plus the butane. We can also use Grignards to do this. This is totally possible. And again, as a base, it's just going to extract that proton here. Deuterium, right, is heavy water, so heavy hydrogen. So this is a way for me to add a deuterium. And again, we've seen this before. The reason that we never react the Grignard in any type of proton source, such as water or alcohol, is because it acts as a base. We can also use these as strong nucleophiles, and this is the one that we're familiar with very much with the Grignard. And so these are all review reactions. Right? We can have a Grignard react with a carbonyl, such as a ketone or an aldehyde. So this will react again as a nucleophile. Right? And then from there, it picks up a proton. We can have them react with epoxides. Right? This one is very useful because it adds to one position and then the OH is on the other. right? So we make a new carbon bond on one position. And again, review reaction, we've seen this before. We can have the Grignard react with CO2. Give the carboxylic acid. We're going to have a Grignard react with an ester. And we can have the Grignard react with a nitrile. Okay, and this one difference here, we're going to finish this one off with H3 plus, so we're acid and water. So remember what we end up here is the imine that then hydrolyzes to the ketone. Okay, so we've seen all of these reactions. Just bringing them back up to memory. In all these cases, the Grignard is really reacting as a nucleophile. So it's got a carbon nucleophile reaction. Because of that, it's important to understand that you're always acting at an sp3 carbon. So if we look at each of the carbons that we're reacting at, right, they're going to be an sp3 carbon. Well, that one's not, that's an sp carbon, but this is sp3, right? And so when we look at these, oh, I'm sorry, this is sp2, but these are carbonyls, right? But if we look at our carbon groups up here, we've got primary sp3s, and that's going to be important when we get into the coupling reactions. Lithium can also do this, but you don't see lithium do this quite as much. Main reason is that lithium would do almost exactly the same reaction, but is much harder to work with. So a Grignard reaction will take, Grignard reagents will take a little bit of water, but lithium reagents will react with water violently, right? And whenever you're in an organic solvent and something reacts violently, that can be dangerous, right? So although these same reactions could occur with lithium, we usually don't show them with them because they're not done, right? So lithium is a great way to use as a base, but it's the Grignard that's most often used as a nucleophile. Okay, so we've seen all those. Now let's go to the other one we've seen, which is our Gilman. So we're starting this chapter with some reminders. Now a Gilman, the way we make a Gilman is we take the alkyl halide, react that with 2 equivalents of lithium to make the lithium salt, right? So we're going to deprotonate that. I mean, we lose the X there. And then that reacts with copper halide, right, to end up giving us the cuprate. Okay, and this is known as our Gilman reagent. Now, the Gilman reaction uses a coupling process. For this first one, all right, so this is a coupling process for acid chlorides. All right, so our Gilman there with the 2 ethyl groups on it. Right, and again, we've seen this before. This was in our acid chloride or acid derivative chapter. The next reaction is an alpha beta unsaturated. And the thing to remember here is that the Gilman's reacting as a soft nucleophile. And so if we take our alpha beta unsaturated, right, we can get a beta addition. And again, this one we saw before. This is a review. So we've already been using some organometallic reactions. This next one is a new one. It is using a Gilman. What's happening in this case is instead of using the acid chloride, we use a Gilman and then a halide, usually either iodine or bromide, to do a coupling between 2 R groups. And so far for our everything except for the strong base reactions, we've been forming carbon-carbon bond reactions. This one's interesting because if you think about it, I could start with this iodide, right? React that with lithium, then react that with the copper halide, that then makes the cuprate. And then I could add another halide. So if I can make a halide out of something, I can do this reaction. Which means that here you notice I did all sp3s, but I can use Gilman's for, I don't know why I changed from black to blue, blue to black, but let's stay that way for a little bit. If I can make the halide out of it, I can make the cuprate, right? So I can make the cuprate here and react that with a halide. So here I have the halide on the secondary carbon, I mean the sp2 carbon. And what I can do here is I can make here I've done a coupling between two sp2 carbons. Okay, so this reaction really extends out the possibilities of what I can synthesize, right? So up to this point, we potentially could add a carbon using the Grignard process, but the Grignard process is limited. When we look at the Gilman, again, somewhat limited, but here when we look at this one, now we're starting to make these sp2 carbons, which is going to change our reaction possibilities quite a bit. We can also do these with aromatics. So I could start with the halo aerial group, add the Gilman, and that will allow me to create a styrene in this case. Questions about these? Okay, we're going to be going through lots of reactions, and most of them don't have mechanisms because we're dealing with organometallic, which you won't get to those mechanisms until you get to inorganic chemistry. And since most of you won't be taking inorganic chemistry, we're not going to worry about the mechanisms on these. So let's go ahead and do a few try this, and we'll break up the lecture today with some try this problems. So giving reagents for these three. Okay, let's go ahead and start a look. Take a look. Okay, on this first one, I'm doing a direct addition to my carbonyl. So for this one, I can use the Grignard. I just need to make sure I use the right Grignard. So we want to have 3 carbons, right? And then our magnesium bromide. And then to get the proton in the second step, I need to add water to the reaction. Okay, so that's just a Grignard addition to a carbonyl. This next one is going to be a coupling reaction. We're adding a carbon. There's several ways we could do this that we'll learn, but right now we only know one, so that makes this easy. We're going to be using a Gilman, and for this one, we need to make sure we show it the right way, right? So we got 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, right? And then the copper lithium. Right? And that's going to give me the coupling to give me this product. The last one here, we're going to do again a Gilman, but this is one we've seen before. So this is a new reaction. The other 2 are review reactions. Right, so here we want 4 carbons. And the copper lithium, right, to make the cuprate. And these are classical. There's one more classical, and we're going to move into some more modern organometallic reactions. The other classic kind of reactions that have been around for a long time is the CHEM3153002. And learning these names can be helpful because you're going to see as we get into the next section, there's a bunch that are very similar. And putting the name, associating the name with the conditions can help you keep them straight. The Simmons-Smith reaction is actually going to use a organo-tin. And like with the magnesium, it does an insertion to give us this organo-zinc, I'm sorry, not tin, organo-zinc compound. And what these reactions do is they do cyclopropanations. And specifically, they tend to use diodomethane plus a zinc copper that just reacts a little faster. The main metal here is the zinc. What happens is I make a cyclopropane. It's a direct insertion. So if I start over here with the trans, I end up with a trans over here selectively. Right? So I have a stereoselective addition reaction. This can be thought of as a carbene type process. With the organo-zinc, the Simmons-Smith, this is the way they used to always show it. Now there's a little bit of consideration, but the carbene, that's what this compound is a carbene, does explain the stereospecificity of ending up retaining your stereochemistry. And cyclopropanes do turn out to be important in some biological molecules. Natural pesticides have these, and synthetic pesticides also have cyclopropane. So this is one way to do that. You can also do this with chloroform in base. The difference here is that our product has 2 chlorines on it. So only useful if you want 2 chlorines on that. And what happens here is that you do form the carbene. This mechanism is well known. You do form the carbene reaction, and then the carbene reacts to give you the cyclopropane, the dichlorinated cyclopropane. Now, forming carbon-carbon bond reactions are very important, right? So if I want to make big, unique molecules, that's something I want to do. So all of these make those. So organometallics make those. So there was a big push for new reactions, and they started looking at palladium catalyst. Right, and the palladium catalyst we look at, you know, we could have 2, and L here is just a ligand. So you saw 2 classes of palladium. You saw 4 and 3, and 2 ligands. And so the the one you're going to see your book use quite a bit is this one, just the acetate, but there's lots of variations. For the 4, the one you'll see most often in the book is going to be this triphenyl ligand, and it's palladium. And so the next class of reactions all use these palladium catalysts as kind of a middle. And what the palladium does, again, we're not going to get heavy in the mechanism, but think about the palladium as something that can add extra ligands to it and then slide those ligands over. So think about it as something that can take in a new ligand, slide that ligand over, right? So it kind of works almost like a little robot that can help maintain structures, right? So if you give it a structure, it can hold it for a little while until you can get another thing, and then that allows it to work. So the palladium complex allows this. So all of these are based around the palladium, and they all have names, and they all have slight variations. So that's where the name and the palladium are important. So the first one is the Steely coupling. Steely coupling is going to be based on 10. So we have an organo 10. Then we have organic halide here. And now this is both going to be iodide, bromide, and then trifolate also works with this one. And then we're going to add a palladium catalyst. And for this one, it could be either the palladium acetate or the palladium triphenylphosphine, the tetratriphenylphosphine. And this gives me my coupling. The Steely coupling can be used with aerials. With our palladium acetate in this case, right? And the steely couplings added in carbon-carbon bond forming processes that really weren't available before. So here we have two aerials being coupled together. Again, we can also use things like a triflate that's shown by the OTF. So the triflate is the CF3. Okay, so we use the tin, the good leaving group, either the halide or the triflate, and then our palladium catalyst. And notice wherever our tin is, that's where we attach it to wherever the halide was. So this is a direct coupling process. So these can be pretty selective. Making the tin reagents is pretty straightforward. Organotin or organostannanes. First, we make the Grignard. And then we add the triphenyl tin chloride. And that displaces the Grignard. We get the stannose. So if we can make the Grignard, we can make the tin compound. Use the palladium and we can get the coupling towards iodine bromide or the triflate. Questions about the steely? So there are some limitations to the zinc. I mean the tin compound. So they came up with the Suzuki coupling. It used organoboranes. So steely focused on tin. Suzuki couplings focused on borane. There are several different types of borane. So we can have one that is dialkyl. We can have one as diether-like. Or we can have one that is just the boric acid style. So I'm going to show you a generic one first. Here we have an R attached to a borane. That's the important part. Our Y can be just an R group, an OR group, right? Or I should probably use primes, or an OH. Right? So we got a little bit of flexibility there. And the reason you need the flexibility is which one is easier to make, right? They all work the same way. And then on our other side, our X, now our X, like the other ones, is our iodine, bromide, or our triflate. For this one, you tend to use the quaternary ammonium, quaternary palladium. So four ligands around that. and you use a base. Right, so something like sodium methoxide. And we get the coupling. One of the common borane compounds is this aromatic species. So we got the borane. React that with a triflate. Again, we use our palladium. So all of these named reactions here at the end are all going to use the palladium. So similar to the steely, little bit difference. One of the differences here is to make the organoborane is that you can start with just a triple bond or a double bond. And then if I add something like BBN, so if you remember, we got this, that's a horrible way of drawing it. This is 9 BBN, right? We used those before, but then after we used 9 BBN, we would add hydrogen peroxide and a base to form the anti-Markovnikov alcohol, which would end up giving us an aldehyde. Here, you just stop. So instead of going ahead and doing the second step of the hydroboration oxidation, you just stop right here. This gives you your organoborane. Similarly, you could start with, let's say, double bond species here, react that with a single hydrogen borane compound like this borate. We lose that double bond, but now we have the borane. Okay. Questions about this one? So Steely is very similar to Suzuki. The next one, Nagishi. This one is an organo zinc. So generically, right, we take an organo zinc, take the alkyl halide or allyl halide, again, put it in our palladium catalyst. Get the coupling. Most of these are pretty similar. There's very, very subtle changes. Because the zinc can be made of the alkyne without interacting with the alkyne. So if we look at the borane would have reacted with the triple bond. So the nishi and the triple bond formation would be favored over the Suzuki because the borane doesn't react. So there's subtle differences in these when you would use one or the other. Now, usually you have to look in a book to figure out when they are, so you're not going to see those subtle differences, right? So I'm not going to ask you whether you should use a Negishi on this one or whether you should use a Suzuki on this one, right? They're very subtle differences. Like a Negishi works better with triple bonds because the borane doesn't react with the triple bond. That's important to know, but again, this is sophomore level organic, so later on you can get to that. So, but the coupling reactions are going to be similar. So Negishi is using zinc, but it still uses palladium. So if we look at these, they're all really using palladium as our one. The last one, the HEC, is kind of the most specific, but because it doesn't use other metals, sometimes it's considered a slightly greener process. And here we have to have an alkane, and not all alkanes will work, but an alkane, we use a 2 palladium. It has to be a 2 palladium ligated, and we need a base, right? So like our Suzuki, we need a base. And what we get here is coupling directly onto the double bond. So here we're not using a second metal. Now, it is somewhat specific. So the R group here has to be an aryl, a vinyl, right? Or a benzyl, right? So I have to, my R group here is more selective. And then my I group here, I mean, I put I, but the X here needs to be either iodine, bromine, or the triflate, which most of these all have that. So if you think about it, I could take this, okay, and we'll get and you usually get the most stable bond. So if we look at these, right, the Suzuki, I mean, the Steely, right, the Suzuki, the Negishi, and the HEC are really very similar, right? The HEC has specific double bonds and aerials that we need to use. The Negishi is using zinc. The Suzuki is using borane, and then the Steely is using tin. They all use some type of palladium catalyst, either a 4-ligand or a 2-ligand palladium catalyst. The borane, the Suzuki, you have to add a base. For the Negishi, you don't have to have a base. And for the HEC, you have to use a 2 and a base, right? So there's some specificity here. The thing to remember is that you're going to get direct coupling. The last section in this chapter is alkene metathesis. And the idea of alkene metathesis is that if I can take an alkene species and run it through a catalyst, I can, and I'm gonna have to color code this. So purple. Oh, wait. Is you start to you switch the groups. And then depending on the catalyst, right, you could do this to always get the CH, right, or the CR, right? So what's happening here is we're actually changing that double bond. So the metathesis is the idea of changing that double bond. Your two main catalysts for this is the grubs. Oh, and two B's, grubs. That's a rhodium catalyst. Oh, shoot. I forgot the other one. I forgot to write it down and I forgot the other name. And the other catalyst, which is molybdenum. Stork. It's like stork. Oh, can't remember his name. So these are the two reactions. And the mechanism, what it does is it kind of brings in and associates to that double bond, and then we get kind of breaking. So if you think about it, I'm bringing them in, I'm associating to, and then I'm deciding that this one gets stuck to that side and goes away, and then this new one, the one left over, goes, and I bring the other one in, right? And so I'm always taking in a double bond, and I'm taking those double bonds, kind of breaking them because of the coordination to myself, the metal, and then I'm hooking it to the other one. So if you think about it, that double bond here, right? That's going to be attached to the next one comes in. And then, so you kind of think about it like one of those, you know, you come in and you're bringing it in, you're moving it over, you're bringing it in, you're moving it over. And what this does then is it allows you to couple these double bond species. So if I take this one with a Grubbs catalyst, right, I'll end up with the two groups attached, and then I'll lose the CH2. You know, if I use the Grubbs here, I stick the two bigger ends together, right? And then what's coming out of the reaction is the small molecule. Grubbs can also be used for ring formation. You have to set it up right, but if it's set up right, it'll work. Schrock catalyst. So here again, all right, the metathesis, I'm actually taking those two sides, those two double bonds that are attached to the R, they get attached to each other, and then the CH2 floats off. In this case, that makes a ring. So the ring formation with the grubs will work for 5, 6s, 7s, right? Normal ring. It'll also work for some really big ones like 9, 10, 11, 12, right? But they get a little bit, small ones is a little tougher. We can also do ring breaking. But with ring breaking, we need to add a driving group, which is we need to add the ethylene, right? The CH2. So we add in the methylene. Now when it does that, this actually drives it forward. So almost all of these are being driven forward because loss of the CH2 is a gas, and that's going to drive the reaction forward. So if we think about the Chatelier's principle, here if we're forcing the CH2 into the solution, then what happens is I'm breaking that ring open. So the Steely, the Suzuki, Negishi, and the Heck, those are all reactions that came around in the last about 30 years. The metathesis, those are really reactions that also came about in the last 30 years, right? So when I was going through graduate school, these were just then being published. So these are relatively new synthetic strategies that actually led to lots of new materials. Some of the materials we have for touch screens or computer screens that on laptops or battery technology came through the synthesis of molecules based on the discovery of these synthetic strategies. So let's try this to finish it out. That is what we're going to cover in this chapter. I'll add up the products. I'll add up the products. I'll put up the learning outcomes so you'll know what to look for. Take a little time for this one. Okay, let's go ahead and take a look at these. Want to do a few of these? Okay. When we look at this first one, right, we've got the tin, we got the palladium. That's our clue that this is going to be some type of coupling reaction. And then what we want to do is we want to look at the position that's attached to the tin and the position that's attached to the halide or triflate. Right. Once we have those two identified, then we just attach them. Right. Make sure that your stereochemistry is the same. And I just was about to make a mistake. So if this is cis, if this is cis here, then my product should be cis also. Right. So I retain that coupling. Right. So wherever the tin is, that's where this gets attached. It's not the case with HEC, right? HEC is going to go with the most stable, but the rest of these, where the metal's attached is where I'm going to couple. Okay. The second ones, I have a grubs, right? So grubs or Schrock, right? If you see these catalyst names, right? This is going to be a metathesis. And what a metathesis means is I'm going to clip those two things and hook them together, right? So when you see a grubs or a Schrock, think metathesis. And then what you're going to do is couple the alkenes. Questions about those? Oh, except I didn't lose my aromatic there. All right, let's do a couple more. Okay, let's take a look. So if we look at the first one, okay, this is going to make the 10, right? And this is the Simmons-Smith reaction. The Simmons-Smith is going to give us the cyclopropane. And so that means I'm going to get my cyclopropane, and then I want to make sure that I maintain my stereochemistry. So if that's trans, right, I need trans over here. If we look at the last one, the next one, right, we got the borane. This is a Suzuki reaction. We've got the palladium catalyst. This is our triflate. So again, if we look at what I said before, once you see the palladium, right, you know that this is going to be wherever the borane, right, and the triflate, that's what I'm going to be attaching together. So that's what I need to focus on, right, and so that's my product. This last one is a review, right? This is the Gilman reagent where we turn an acid chloride into a ketone. All right, so the quiz, just so you know, before you get into it,